Good morning, everybody. Hopefully everybody's doing well. Today we're going to go through the final section of our sound chapter and go through the different applications of sound as well as how acoustic instruments work. So here we go. First application of sound is talking about sonar or echolocation. Sonar can be used to map anything, right? So a sound is sent out, it hits a boundary, it comes back to the source of the sound. So it's detecting how long it takes sound waves to go out, hit the boundary, and come back. So they're reflected sound waves, and we use those to map a certain location. Ships will use them to map the ocean floor, and certain animals use the same process called echolocation to see where they are going. All right, here's a couple different pictures of different animals, right? Bats use it, dolphins use it, other certain types of fish use it, and any ships or submarines will also be using sonar to map their surroundings. So again, sonar is just sound emitted from a source, it hits a boundary and comes back, so we have a reflected wave, right? And how much of that reflected wave comes back can tell us how big the object is, and the time it takes for that to get back tells us how far away it is. The other application of sound that we can talk about is an ultrasound. Ultrasounds are used in medicine to map the same way sonar is used. It's just a much, much higher frequency. We're talking frequencies that are in the millions of hertz. Those outputs, those maps, are called sonograms, most frequently used for pregnant women, right? They map or show the picture of the baby, but they're also used for a variety of other reasons to evaluate soft tissue. We use ultrasounds because the sound waves are not harmful like X-rays are. Here's a couple of examples, right? Sound waves are used to produce images, and they're super high frequency, right? And again, not damaging to anything inside. And now they can produce 3D sonograms. That's an unborn baby. The last thing that we're going to talk about is acoustic instruments and how they work. All right, acoustic instruments are going to rely on standing waves. We briefly talked about them last section, right? Standing waves are when constructive and destructive interference are both happening at the same time. Now, we can only set up standing waves in instruments relying on those certain frequencies, which are the notes that are played. So basically what's happening is if we play a note, that note is called the fundamental frequency. That fundamental frequency, remember hertz, has a wavelength that's twice the length of the string, if we're talking about a stringed instrument, or twice the length of the column of air, if we're talking about a woodwind instrument or a trumpet or tuba or something like that. So fundamental frequency is the frequency of the note that's being played. And here is sort of a graphical depiction of a stringed instrument, right? If the string is this long and we play this note and the string is allowed to vibrate back and forth, right, between one end of the string and the other, that string length is half of the actual wavelength of the wave that we are playing, right? So that is called the first harmonic or the fundamental frequency. First harmonic and fundamental frequency mean exactly the same thing. So talking about harmonics, harmonics tell us or show us the quality of the instrument that we are playing. Harmonics produce multiples of the fundamental frequency. So if we are playing a note that is 200 hertz, and that is the fundamental frequency, the second harmonic would be twice that, the third harmonic would be 3 times that, and so on. The reason why a tuba sounds different than a violin playing the same note is the harmonics of the instrument. I'm going to show you that in sort of a depiction in a second. So again, if we're talking about the first harmonic, right? The first harmonic is the fundamental frequency. That's the note that's being played, right? If we wanted to map or show the second, third, fourth, fifth harmonic, those are all just multiples of the fundamental frequency. So let's say this instrument that we are playing this 200 hertz note on produces all of these harmonics. If we put all those in together, we get the sound that comes out of the instrument. That's what this composite waveform is on the bottom. Now, what's not really shown here perfectly is each harmonic as we go down is softer and softer in volume and amplitude, right? So the first harmonic would be louder, the second harmonic would be a little bit less, and so on down the road. So our composite is a blend of all of these sounds that the particular instrument is producing. And the very last thing is something called resonance. Resonance is when the vibration of one object causes the vibration of another to vibrate at what are called natural frequencies. All right, so if we have a stringed instrument like a guitar, and you pluck the string and we play a good note, that string's going to vibrate, but then it's going to cause the body of the guitar to vibrate also. All right, the same thing with any wind instrument. All right, if we play a good note, if you've ever played acoustic instruments before, you know the difference between playing a good note and one that wasn't quite as good, right? The really good notes that are played sound nice and loud, sound full, right? That is happening because resonance is happening inside of the instrument, right? So we were vibrating the instrument at one of its natural frequencies to produce a nice loud sound. And that loud sound comes from the string being vibrated or the air inside the tube of a wind instrument being vibrated. At the same time, the body of the instrument is being vibrated also. This can also happen with other things. You may have seen this before, right? We take two wine glasses. All right, if we vibrate it at one of the glass's natural frequencies, it'll resonate and produce a nice loud sound. Different water levels, we can produce different sounds. Right, that's an example of resonance. So we're vibrating the glass, which is vibrating the water down there and producing sound inside of the air in our wine glass. Another picture that we can use here is the tuning fork versus the flute versus the violin, right? We use tuning forks for a reason. All right, here's a tuning fork. It says F. All right, so this is an F, and the frequency on it says 349.2 hertz. All right, so the tuning fork, let me move myself out of the way here, right, will only produce the fundamental frequency. It will not resonate at all. All right, it's not going to produce any harmonics. Sorry, it does resonate, no harmonics. All right, so if we vibrate the side of the tuning fork, it's vibrating between the two metal forks and producing a nice loud sound in that air in between the two forks. That's what resonance is. If we look at the flute or the violin here, they sound different. They produce a different sound, even though they're playing the same note, because of their different harmonics, right? So again, tuning fork can only produce the fundamental frequency, right? If we're using F, here's an F. right? So, which means that would be the fundamental frequency. If we double that, that's a second harmonic. If we triple that, that's the third harmonic, and so on. So hopefully that all makes some sense. Any questions on that, let me know, and we will talk to you next time when we're going to do a lab on resonance and figuring out the speed of sound in your room or in my room.